Hi there. In this video, we're going to be going through the data types in IV. So without further ado, let's get started. Yeah, here are all the data types supported in IV. There are 4 integer data types depending on the number of bits used to represent the value. There are 4 different types of unsigned integers, which basically are integers which don't have a sign, so they're only positive. Again, there's 8-bit, 16-bit, 32-bit, 64-bit. We then have bfloat 16, float 16, float 32, and float 64. Yeah, the bfloat is just, from my understanding, a different way of representing the floating point data. So it just uses a different underlying representation. And yeah, I actually don't know. You'll have to Google kind of what this is useful for, but it's something that we support. And then Boolean as well. Okay, so basically these data types are all defined at import time originally. So we have all of these data types defined here, and yet we give them, we instantiate them with these IV data type classes, which are actually incredibly simple classes which just inherit from the string, and effectively during the new special method where we create a new instantiation of this, we just do some simple checks to assert that the string has the correct representation. So you can kind of imagine these types as being a subset of the string class where there's only a very particular set of strings which we can represent. I think these are defined, they're defined here, perfect. So we have this, like the int data type, it inherits from the data type, which itself inherits from the string. The data type just is anything which contains an integer, or float, or bool in the string. We could also do assertions for the numbers of bits, but I don't think it's strictly necessary. Maybe in future we'll extend this. Int data type is something with int in the string, and float is something with float in the string. Yeah, maybe at some point we'll increase this assertion to make this subset even more explicit, but yeah, I'm not sure that's necessary right now. So that's these, and then we also have these native data types, which I'll explain in a moment. Okay, so yeah, each of these is a data type instance, and again, it derives from a string, has very simple logic in the constructor to verify that the string formatting is correct. All data types can be queried as attributes on the IV namespace, such as iv.float32. This is what this enables. We are actually now in the init file, so the fact that it exists here, by definition, means that we can access this from the IV namespace. Okay, so yep, so then in addition to those, we also have the native data types. So likewise, these are also specified at import time. They're all initially also set as data type instances, which I think, yeah, we saw already. So here, they're initialized exactly the same. And then there is also this native data type class, which is initially defined as an empty class, as you can see here. Now, in a similar way to how we do things with other things, such as the native array and so on, we actually then overwrite these when we're setting the backend. So the native data type is overwritten with a specific version, such as torch data type, etc. And likewise, the native data types here are also overwritten with framework-specific data types. Actually, I think I explained that a little bit later, but I jumped the gun a little bit there. So the following tuples are also defined. So we have all data types, all numeric data types, all int data types, all float data types, which are again defined in the IV init file. And in this case, it's kind of, this is everything. This is everything, everything apart from bool, actually. Then all the integer, both uint and int, and then all the float, etc. And then we have these as well, invalid data types, valid data types. And again, because this is IV, we're initializing to say that nothing is invalid right now, because no backend has been set, and everything is valid at this point in time. Okay, so that's all of those. Yeah, and then this is what I then touched on just a moment ago. So when a backend framework is set, then some of these are updated. So as I said, firstly, the native data type is updated with a backend specific data type class. In this case, for example, we have torch data type, which overwrites it. Yeah, so that happens first. Secondly, each of the native data types are replaced with the true native data types. So again, like we have torch.int, torch.int16, etc., etc. So we update all of these as well. But the Ivy data types remain as they are. They remain strings, which enables us to, still kind of do things in a framework agnostic manner. If we call ivy.float32, this will still be the string. It's only then if we do ivy.native float32, then we'll get the native version. Because even when a backend is set, ideally we still want to be doing everything in a framework agnostic language that has a consistent representation and so on. Okay, and then the valid data types are also updated, and also the invalid data types. So again, I think we use torch as an example. These strings are updated to the valid data types, the valid numeric data types, valid int data types, and float data types, and likewise all of the invalid data types as well. And in this case, for example, we can see that for torch, the unsigned integers with more than 8 bits are all unsupported by torch. So uint16, 32, and 64 are all unsupported. So we add them all here like this. But there's no invalid float data type, so this stays empty. Okay, so and as we said, so Ivy float32 will still reference the original definition here as being the Ivy data type, whereas Ivy.native float32 will now reference the new definition, which is provided here, like we just saw. Yeah. Okay. So these tuples, all data types, all numeric data types, etc., are also left unmodified because this all is effectively referring to everything that Ivy is able to represent irrespective of backend. So this doesn't change when the backend changes. Even in the case of a torch backend, we still include all of the unsigned integers in all data types and all int data types. And this distinguishes these lists from the valid and invalid lists. Okay, so yeah, and as we said, importantly, we must ensure that the unsupported data types are removed. So uint8 is supported by torch, but none of these are. Therefore, after setting a backend using ivy.setBackend, we should no longer be able to access ivy.uint16. This is quite important for a few reasons. I mean, first of all, it doesn't make sense if when the backend is set and this data type doesn't exist anymore. Basically, with this backend, if we can still call ivy.uint16, that's very unintuitive. It also causes failure in the array API test suite because the way that they determine supported data types is exactly by checking for these names on the namespace of the framework. So that will also cause failures, and therefore we need to remove them, which is basically handled by this little piece of logic here. We go through all of the, and this is explained in more detail in the backend setting section, but basically what we're doing here is if this key is in the invalid data types, then we need to remove it from Ivy, basically. Just to solve this problem when data type setting. When we then unset the backend, it's added because we always keep this Ivy original dict wherever it is. We keep this global variable initialized at the beginning, so we don't like lose it. We can reset it and add it back, but when a backend is set, we remove them, basically. Okay, so that's that. So that's just kind of how data types are handled, where they're defined, how they're set, and how they're overwritten, etc. So now, let me just quickly jump ahead a bit. Okay, yeah. So now we can talk quickly about the data type module. So the data type module provides a variety of functions for working with data types. A few examples include ivy.asType, which basically copies an array to a specified data type, ivy.broadcast2, which broadcasts an array to a specified shape, Actually, just to quickly say, I think this is a strange function to be included in the data type module. It's dictated by the array API standard, but I don't see exactly what broadcasting a load of shapes together has to do with data types, but we're sticking to the standard and we've added it there as well, but that's quite a curious one. And then we have another one which is data type related, which is result type, which returns the data type that results from applying the type promotion rules to the arguments. So this is very, very relevant. And yeah, an important point to make here, which references back to the function types section, is that many functions in the data type module are convenience functions. And this basically means that they don't directly modify arrays themselves, and they generally kind of give us information about the data type of an array or something like this. Some of them do. For example, as type, it does modify the array and therefore is not a convenience function. This is something that is part of the computation graph, but many others don't. For example, the following, like can cast, just gives us Boolean results on whether data types can be casted together at all. Ivy.datatype returns the data type, so it kind of gives us a string representation from the array, which won't be part of the computation graph unless, no, this won't be part of the computation graph, so yeah, this is always a convenience function. Set default data type is about setting a global value across the project, so again, more of a convenience function than kind of an array computing function and so on. And default data type, again, does something similar, just returns the default data type, which is set system-wide. And this is probably the most important function because any function in our Ivy functional API which receives a data type argument in the input will make use of this function under the hood, as we explain in the next section. Basically, and this is the most complex part of the section, so we're now going to explain how we handle data types in any function, and how we do this with some decorated logic and wrapping logic, which kind of solves this for every single function in one place without us needing to keep re-implementing the same piece of logic. So the first thing is that all data type arguments are keyword only. All creation functions include a data type argument, which is then specifying the data type of the created array, obviously. Some other non-creation functions do also support the data type argument, such as ivy.prod and ivy.sum, which do reductions across the array, and therefore when we can potentially be getting very large results or at the end, then we might want to specify what happens in the likelihood of overflow errors, and therefore we might want to explicitly upcast the data type bits ahead of time, which is why this is added into these functions. And again, this is actually an array API standard decision that we're following, which makes a lot of sense. And then, exactly. So the non-creation functions which support it are generally functions that involve a compound reduction across the array, which could result in overflows. And this is exactly the rationale behind adding it for these. So the data type argument for any function which supports it is always handled in the inferred data type wrapper. And basically, I can quickly open this up. What this does is it uses ivy.default data type under the hood in order to determine the correct data type. And as we discussed in the function wrapping section, this is then applied to all applicable functions dynamically when the backend is set. So basically what happens is we take in the original function, we then create a new function which has the data type unspecified. And basically what we do is we find, so first of all, if data type exists, nothing's required. We've been explicitly provided with it, and therefore we don't need to infer it from the global default or anything. But if it doesn't exist, then the first thing we do is we get the first array from the arguments, and then we infer the default data type using the data type that's been entered into the array if it was provided here, and also we make sure that we return it in native form. And this basically goes through a few steps. Of the data types provided, we infer it from here. If there is an array in the inputs, we infer the data type from the array. If there's no array in the inputs, and this isn't provided, then we'll end up just getting the globally set default. And that will be the case in the case of a creation function, for example, where there's no arrays at all, and then we just need to get the global default, basically. And then we call the function with the data type now set, and the backend function itself then essentially has a requirement for the data type to be specified and has no default behavior, which is why the backend function then would not have data type equals none, but it will actually require the data type, and it will always be set because this decorator will make sure that we're always explicitly providing a value to the backend function. Okay, and then this is just going through that whole process. So, yep, so we call this, and basically if the data is provided, we use it directly. Otherwise, if there's an array, we infer it from the array. Otherwise, if a relevant scalar is provided, then we set array to the scalar. And actually, in this case, we can't actually, add the inferred data type decorator because we need to actually explicitly provide this item equal to the relevant scalar. And this wrapping logic at the moment can only do this for the first array. Whereas in a function like ivy.fill, we might actually need to infer the data type from the fill value. And this piece of logic wouldn't be able to handle that, and therefore we should not use the inferred data type decorator, and we should do this manually instead, which we explain here. And again, another one is the start in the arrange function. This is a relevant scalar. But ones that are not relevant would be axes or dims, etc., which must always be integers and are therefore not informing us anything related to what the data type of the returned array should be. So they are like irrelevant scalars. Okay, so that's this. And again, if nothing is provided, then we just use the globally set data type, basically. Okay, so for the majority of functions which defer to infer data type, for handling the data type, these steps will have been followed, and the data type argument will be populated with the correct value before the backend specific implementation is ever entered into. Therefore, whereas the data type argument is listed as optional in the Ivy API function, kind of in this kind of file, the argument is listed as required in the backend specific implementation. So looking at zeros as an example, in the Ivy creation file, we have data type equals none, whereas then when we go into the backend specific implementations, data type is required. And this is how we handle it, because by the time we enter into this function, the decorator has populated the value, and therefore it will always be provided by the time we enter into here. So it doesn't need to be listed as optional. And it makes it very clear that the backend specific functions are only entered into once the data type has been determined. But yeah, for some functions, we don't have the inferred data type decorator, as we explained before, because this decorator can't determine the data type from relevant scalars, such as the fill value and fill. So in this case, we don't add the decorator, and therefore we need to actually handle everything in the backend function. So let's take ivy.fill as an example. It doesn't have this decorator, so therefore the data type isn't automatically handled and set, and therefore the data type does have its default value of none in the backend, and we need to actually do all of this logic. Ivy.default value, data type equals data type, item equals fill value, which again is this scalar here, and as native equals true. And for example, this means that if the fill value is an integer, then we're going to be using the default integer. If the fill value is a float, we're going to be using the default float, etc. And as I said, this behavior can't be captured here, and it's not super easy to programmatically add because we need to kind of understand which integers are relevant and which are not relevant, which is not super easy to kind of add general logic for, which is then why we do it this way. Okay, but the implementations of all of the backends follow a similar pattern to this PyTorch implementation. Again, they all actually do have it provided as optional, and they all do handle this logic explicitly in each backend file. Okay, so then the final little section is basically some backend functions have an attribute named unsupported data types, which flags data types which this particular backend version of the function doesn't support, but other backends might do. So again, this is quite important to note that this is different from ivy.invalid data types, which consists of all the data types that this backend doesn't support at all, and therefore every function with that backend doesn't support the invalid data types. But these unsupported data types, which are function specific, they're backend specific and function specific, are for the other unsupported data types which aren't included here, which additionally this backend and this function don't support. Yeah, and there isn't a link to an example here, but you can see them dotted around in a lot of places. I mean, I can quickly show you, for example, in Ivy, functional, backends, torch, element-wise, I'm sure we have some examples, although maybe not at the time of recording. I'm actually at an old commit hash here. But yeah, there's definitely a lot of these. Yeah, so just for example, yeah, unsupported data types float 16, for example, and this is quite common. Okay, so that's that. Okay, so hopefully that provided a bit of an overview on how data types are handled in Ivy, why we use a decorator and wrap functions to handle a lot of the data types, how we overwrite the data types when setting a backend, and how we use this unsupported data types to flag combinations of backends and functions that don't support certain types. So hopefully that was useful. Thanks a lot for watching, and I'll see you in the next video. Bye for now.